Thank
So
you.
yeah, so okay, there. So I'll I'll share my screen. Uh, okay, so I called the workshop, before starting, everything should be in order. It's about data quality control. Um, meaning before you start analyzing your data or modeling, make sure all the data is correct and in order. That's the main message. Okay, so yeah, you already presented me. So just yeah, you pronounce my name Shachar, J like in Espanol. And yeah, you saw that the workshop will include exercise in R. I wanted to translate it to also to Python, but sorry, I didn't have the time. So, and I hope you downloaded um, the zip file that contains the R codes and even this presentation and some files, some data files. So first, why is data preparation important? First, to make sure your data is correct and accurate. This is the most important things. And then to avoid GIGO. GIGO is a shortcut for garbage in, garbage out, meaning that if your data is inaccurate, has mistakes, or is, in other words, contain garbage, then the output of your analysis or your model also will have garbage. So you want to avoid that, and you want to avoid rework, because this part of the project is a tedious work with all the data and arranging it. You don't want to redo it again. So do it once properly, and you will not have to redo it again. So that's, I think, the main points that why it is important. And when I was a teenager, I worked as an apprentice in a metal shop, and my mentor, my master, told me before start the work, make sure your work environment is clean and tidy. And that's one thing. And the other thing is that you want to invest time in making tools to perform your assignment. It will pay off since you may have to repeat the task again. And these things are relevant also to project with data. You want to make sure your data is in order and correct, and also invest in tools. During my time in the industry, I was, among other things, ERP project manager. ERP is enterprise resource planning, is a software that the organization uses for all the orders, sales, items, inventory, and so on. So also I dealt with a lot of data, and I learned that mistakes in data might result in high cost. So again, it's very important, not only in the industry, but also in science and research, that you minimize the mistakes in data. So the things we are going to go on is mostly are really not very complicated and quite trivial, but still it's important to emphasize them. So one slide about the discussion whether we use Excel or R or other programming software. I don't know if you see it on the screen. Okay. And then we go on to dealing with text and categorical data, then date time data, continuous data, and in the end, correction of biased data. So Excel is a great software. You arrange your data, you order it, you calculate something and make a pivot table and so on. But There's a few drawbacks. Some of the functionality is too automatic and may yield errors, so you have to be vigilant. And the main thing is that sometimes you receive new data or revise data, and then you have to redo many of the operations you did in the first time. You have to redo it again and check it again. So from my experience, write a code to arrange the data. In this way, it will be easy to apply it to new or revise the data that you receive. And you can do many of the quality control inside the code. So that's what I tried to say before about tools. This is a tool, much better than, programming is a tool that you prepare so you can make the next time you need to do it's much easier than to do it with simple tools like Excel. So later on, of course, I think we can open it to discussion, and you can share your experience. My experience as programming is, in most cases, okay, not in all cases, is much better. So yeah, let's go to the first more issue, categorical data. So text data is prone to many mistakes, misspelling, typos, unusual characters arriving from different systems, and more. And what I found is that the main tool to find discrepancies is merging tables. It is merge command in R, and maybe in Excel it's like a VLOOKUP, but it's has much better options. So usually you will do merge with table X and table Y, maybe defined which, if the columns are not in the same name, so you would define which they are. And it's important to define the all parameter, all true or all X true, or maybe all Y true, depending on your order. But for this purpose of data QC, you must use the all. Don't omit it. Otherwise, all the data that you are the problematic data will be filtered. So yeah, we'll go to exercise 1. You can already, at the background, open it with your R. You have two tables. You have species table with the quantity found in a monitoring survey. This is one table, and you have a table of species categorized into groups. This table is let's say, the correct information. It is tested against a taxonomical database. So we're going to join the tables. And I think if you are not familiar with the merge operation, so try the merge with different options of the like written here, and look for the number of rows as the result of the table. And look where does NA values appear. Now I'll switch to the, okay, do you see the R? Okay, so in all the exercises, the first two rows is just to make sure that the directory is the one that where you save the files, so we don't have problems locating the files. And then I read the first table and look at a few lines from this table. You can see in the bottom here. Okay, it's the scientific name accepted is species name, some other details, and the group that we want to add into the NM. Oops, sorry. Okay, this is the second table. Includes the net ID, which it's like a fishing net, and the species that was collected in this sampling, and some details about these, how much individuals and weight and so on, and depth. So we want to merge those tables together. So this line merges together with the field. In the first table, it's a scientific name accepted, and the other one, the species. And we want all the records from the second table, from the table NM, which is the national monitoring, from the monitoring file to appear. So I run it, and if we look at the table here, this is the joint table. We can see that there are many. The scientific name is always the table that we join upon, and contains all the species from both. Okay, just a minute, Sid.
Sorry, Shahar. I think we
Yeah.
have a question.
Yeah, maybe we'll stop because if
No, sorry, I accidentally raised my hand.
Okay.
Okay.
So, but you can do unmute and barge in and ask questions, or tell me if you don't understand something, or it works differently if you downloaded it and so on. So you can see that the items that appear in the national monitoring file but does not appear in the species list has an NA. So now if you want to try and find the more analysis in the bottom of the code, I always also in the other exercises did some what I call cheat sheet with some more code to analyze it a little further. Okay, so if you want to find out which are the items that the species that does not appear in the species list, the species group list, but only in the monitoring, so you can handle it. You can write your own code here, and I'll give it a few minutes. And in addition, you always many times want to see if there is duplicates in your data. So if you do just some duplicates gives only it's a proof, it's a logic results. So if I sum it, I get, yes, I have one. If in the bottom you can see I have one duplicate, and when to consider what to do with it. So I'll give you maybe a minute or so to look at the data. In the meanwhile, just let me go back to the presentation. Okay, so try to see what did you find? What is the problem with the data that not all the species is in the national monitoring file appears in the species list? What are the mistakes? And can suggest how we can fix that. Anyone wants to share any findings or suggestions about this data? Okay, so I'll continue, and I hope it's okay if it's. Let me know if it's too slow or too fast. Um, Here I just put a line that table that gets all the items that has NA in the group field, which means they are in the national monitoring, but does not appear in the species list, and then we'll print it. And the bottom, so you see there are maybe 20, almost 30 species, but most of them has the ending SP in the end. So probably the species list does not have this SP, and also some with numbers, some with the OTU. And so if we omit, I substitute all the numbers with empty string, and all the SP and all the OTU with the empty string in the data, and try to merge again, and look again at the items without groups. Now it's much smaller. It's such a smaller group that I can handle and see each of them of these species. Is there a spelling issue, and so on. And for the question is how we correct it. Let's that's really an open discussion, because can be many scenarios which you can decide. I want to fix it in the source in my data, or if I have, I mean, next time, next sampling season, I'll get the data, and again, it will be a mistake. Maybe I'll build some table um, to fix, I mean, to correspond between errors and the right name or something like that. So that really depends on what you expect from your data in the future. And if we look at the duplicates now, I see which items are duplicate. So I see one record, which appears exactly twice with all the same date, the same net ID, and the same species, appear twice. But still, it is a question. Um, it is a question if it is a problem or not. So I have to go to the person who made the sampling and discover maybe the same net. He counted one species, and then when he continued, we found another in the same net, another species, and wrote it in a separate record. So it can be real, or it can be sometimes a mistake. So but you should check it. Check for duplicates. Okay, that's about, I think, categorical data. If anyone wants to comment or ask, text data or categorical data. So again, the main tool is the merge command. Now, datetime data, I will not do an exercise on this part, just a recommendation from my experience, because there are different formats of date, and sometimes it is a nightmare, especially if it's in one file, there is more than one format, or it might be a nightmare to convert them. My suggestion is always to convert the date to ISO. ISO is International Standard Organization, ISO 8601, which the format is 4 digits to the year, dash 2 digits to the month, dash 2 digits to the day, and then the hour, minute, and seconds. I recommend sticking to this standard. It's unambiguous, and it will order correctly also as text, if the year and the months and dates. I'm sorry about the American guys, but for me, it's a weird American method, which months at the beginning, and sometimes they have difficulties counting to 24 hours, so they add the PM and AM. So I suggest really to avoid it. And on the right side, if you are working with Windows and you really concur with this suggestion to turn to ISO 8601, I recommend you to change your system to this method. And then, for example, if you work with Excel or other software, it will be the default format for date. And one more thing is that remember time zone issues. If you download, if you have your data on your lake, usually it will be on time. If you download, let's say, meteorological data from some international data, you have to look at the time zone. Does it have the daylight saving time issues and so on? So it's also an important issue. And if you convert a lot of dates, I recommend the package Lubridate in R, which is great for all the handling of time, data and time. So that's what I have there. I also, what I try to do, but I decided not to do an exercise because it's a little more complicated. You can always, I try to use an AI, let's say ChatGPT, upload a file with different formats with dates with different formats, ask him to turn it, and usually it does a good job. But still you have to look at it, because sometimes the date format might be confusing. Okay, so now for most of your data is continuous. So my recommendation is check your data. Is it what you expect? So you have to look at it in different ways and see if it corresponds to your expectations. Look at mean, max, and missing values. Plot your data. We'll do three exercises about it. Plot your data. Focus on suspected areas. Plot histogram or box plot of your data. And then we'll see that violin plot, which is another kind of box plot, but of the data distribution, might also give some surprising insights. So let's start with the exercise. So exercise 2 contains the data of daily lake level. It's for Lake Kinneret. So level is in meter above sea level, but the Lake Kinneret is below sea level, so values are negative. So just for you to understand. In general, lake level is expected to be smooth. It's unlikely that there will be sudden lake level drop or rise in one day. Maybe if there is a lot of rain, then it might raise a few centimeters, but usually it's relatively smooth. So plot the data, find suspected data points, and zoom in. And can you guess the cause of the unlikely data point? So we just go to just a minute. The second exercise, we clean. Oh. Hmm. I hope I have the right. Doesn't seem to be the last letter, but I hope, but I think it will work. Some missing lines. So yeah, the data contains date and level. And if we plot the histogram, okay, you see that relatively it seems okay, not very suspicious, maybe not uniformly or normally distributed, but there's not too much anomalies. And now we'll plot the whole series. And um, okay, can you see? So every year in Lake Kinneret, in winter you see it's a little shaky, and then when the streams are running, mainly the Jordan River, it fills the lake, and by the end of by spring, um, the lake side, the evaporation is much higher, so the level drops and so on. But you can see here, I don't know if you see my mouse, in the 2014 sometime, there is a strange line. So you can, again, I'll give you maybe 1 minute um, to try and find this strange line, the problem with the data.
Sahar, we have a
Yeah,
question in the chat.
in the
On
chat.
code line 7, the question is what is type is equal to L?
Type L is for the plot is a plot line. If I remove it, it will plot like dots. and it is more difficult to see. For example, this anomaly that you can see here, it's much more difficult to see. And in the line format, it's easier to see. So if we focus around this date, define the start date and end date, and limited the data between those dates, okay, somewhere between 2014 and 16, we can see the strange anomaly, and we can focus even further. We know already it is somewhere in the summer of 2014. Definitely seems odd. And if we just look at the data in this time, okay, here on the bottom left, you can see that the level drops. Yes, it's negative, so it drops a little deeper, and then it's 212.04, and I think you can guess that it was manual insertion of the data and not automatic, and then someone wrote 04 instead of 40, and then you receive this strange anomaly. So that was one example. Let's take another example. Load data for salinity in the middle of Lake Kinneret, and plot the overall data and also distribution. And then you'll see in the code I have already identified suspicious data points. So go ahead and plot it. And then say, what do you think? Are these data points valid? So let's go to the third exercise. Clean again the everything. This time I have to use, I'm using also, sorry, ggplot, because we need a little more sophisticated plotting. So I load the chloride file, I turn it into the date and look at the header. So
como mandaron unos scripts, entonces él como que va corriendo el script, pero
okay, if that was a question, it was in Espanol, so I didn't understand. So we have this file contains the date, depth from lake level and down. 0 is on the surface, and then deeper, and the chloride concentration in milligram per liter. So let's look at histogram of the depth first, and we see that we have very uniform data. I mean, that there is samples from all equally from all depths. Only on the deeper part of the lake is less data, because sometimes the lake level is shallower than 46. So with less data there. Let's look at the histogram of the measurements of the chlorides. Also looks pretty nice. We don't have a very extreme points. And if we plot the whole data, it's the whole data for all the depths per time. And here we can see a few things, interesting things. First, that we have a data gap between around 1990. We have a few years that has missing data. And then we also see that there are like drops of the salinity with low, relatively sudden drop of salinity. And this is something that is odd. But again, the data here is also contain depth. So let's try and plot it with the tile, Geom tile with ggplot for the whole depth. Let's see if I'll try and zoom it, maybe it will be better. So in this kind of plotting, it's much more difficult to see problems because color is not as clear as lines. But you can see that you have like in 2010 some dark color in the middle, and also some other points, mainly on the top left, also strange dark line in the middle. But then it's really more difficult to see in colors. So now because it's a little bit more longer than what we can do in a workshop, I already prepared some points that are looking strange and we want to focus on. So first I'll just focus on these depths, 35 and 30 meters below the lake surface, and between two dates, between 2009 and 2012. Let's plot again the chloride, and we see that there is some strange drops in salinity. Now I prepared some six interesting points to look at. Prepare a table from it, and I run it with a loop to read all of them. Let's look at it. So we see a drops of salinity in those specific dates, most of them in depth of 40 or 30 meters below the surface, and the one on the top left is actually almost in the surface, in 1 meter below. Let's just go back to the presentation for a minute. Okay, this is the data. So the question is this data a mistake, sensor malfunction, or real results? And of course, it's really a question. And then what I did is I showed it to when I found this, that was a few years back, consulted with an expert and said, okay, it may be real. So let's see, because what happens in, I don't know, probably maybe in other lakes also, but in Lake Kinneret, the Jordan River is it's not very saline, mostly from rain. And if it is colder, then the temperature of the lake, the water from the Jordan goes directly to the lower levels of the lake because it is colder, denser, and goes to the bottom, and then may dilute the salinity of the lake. So I already identified in the code. We have file with inlets, which it's inlets of the Jordan River. It has a flow, temperature, and salinity, but we'll use only the flow. And I already defined it, and I want to see what are the flows of the Jordan River in these dates, these 6 dates that I plotted for the salinity. And this is what I did in the next plot. Just overlay okay, just an overlay of the Jordan flow, which is in blue, and the salinity for the same dates. And we can see that each time there is high flow in the Jordan, almost each time, there is drop in salinity. High flow in the Jordan River and drop in salinity. So very interesting phenomenon. In the middle of the lake, is the stream, the water from the Jordan River reach and all the way over there and dilute the salinity. So all of that was true, was not a mistake in data, but real data, correct, except for the top left one, which is all of those in the right are also in the, let's say, winter spring time. Okay, somewhere between January and March. And the top left, it is in the summer, in someone in between June and July, and in 1 meter. So it's probably some mistake, sensor mistake or other. Where's the pistol? Well, wait. Sorry, just a minute. Okay, that's my. Okay, so conclusions in that part, consult experts. Sometimes the odd values are reality. But it is, you learn a lot from it, just looking at the extreme or odd values.
Shahar, we have a
Yes.
question in the chat. Why some high flow peaks didn't lower the salinity? I think you mentioned that it could be also sensitive loss, but I'll let you answer the question.
Well, I just want to take a note. I do not see in my screen the. Can you repeat the question? Why is some of the.
In some high flow peaks, the salinity is not lower.
It's difficult to say without testing, but again, the temperature of the water itself in the Jordan River have to be lower than the temperature of the lake. So if it is lower than the lake, then it is heavier, more dense, heavier, and go to the depths, to the lower levels of the lake. Otherwise, it will go on the top. If it is the same or same salinity or same temperature, sorry. Because the temperature has much higher influence on the density of the water than salinity. So 1 degree below the lake, below the temperature of the level, it will go down. Otherwise, it will go up. So probably I didn't test it in this incidence. Probably other dynamic properties of of the stream of the lake. I mean, I measure in one point in the middle of the lake, but maybe it is a more going a little around the water from the stream, not always straight in the middle. So there have been maybe many reasons. And I only discovered it because I looked into strange points on the data. I wasn't aware of it before that. So it was a good lesson. So let's go to another exercise. Again, we load data for Jordan River temperatures this time, and again plot the overall data and distribution and look for unreasonable data. Okay, remember that Lake Kinneret is a subtropical zone. And then we'll plot a violin plot and see what's going on. Okay, so I remove okay, so the table contains the name of the inlet. This time I think there is more than just a Jordan, but also other streams that go into Lake Kinneret. Date, temperature, and data source. We may have different some different companies, or the data came from different sources. So first, a histogram. Someone sees something that is not logical. You can barge in. Feel free. Okay, if you can see that there is something that close to 0 degrees, which is not really logical. Also, if we plot all the data, let's just a minute. Zoom, you can see also a few things. First, of course, easy to see the yearly fluctuation of the temperature, but you can see some strange data, too low points at mainly in around the 1980s, and you can see more dense lines after 2010. This is because we have more observations there, maybe even hourly. You can look at it later. I mean, just by looking at these plots, we can learn a lot about the data, and then missed one. And let's make a box plot. You can also see that we have few streams involved. And you can see the Jordan and the Meshushim streams. In the bottom, there is a point, meaning that there are extremes that, again, 0 degrees is not logical. And okay, of course you have to know, but and Sheva and this is underwater flow, hot springs. So also temperature is fairly logical that it is hotter than other streams. So again, there is unlikely, we saw that there is unlikely data points. That we should look at. And also I said in the beginning that sometimes box plot is very nice. You can see easily the exceptions or the high or low values, but violin plot also sometimes interesting. So this is the violin plots by the same as the box plot, but we see also a little the data distribution of each inflow to the Kinneret. You can see the green in the Meshushim looks a little strange distribution. So yeah, let's look at it on this strange data. First, there is not very logical that there will be temperature below 4 degrees. So I print all the temperature, the records with temperature with low temperature below 4, and I see that they are all zeros. So of course, temperature 0 is not logical, especially not in a subtropical lake. So I have to take these out. And now for the strange odd-looking distribution. Let's look a little closer, only on 3 streams, the Jordan, Meshushim, and Yarmukh, with the violin plot. Okay, we can see that this is the Meshushim stream is very strange. Okay, the Jordan also not very great, but this is really strange. And if I do the same plot by doing it by data source, okay, plot only the Meshushim stream and plotting it by data source, this line. So I can see I have a problem with only data source. Only one data source has this strange data distribution. And if I print this data, I look at only, in this case, only unique values from the Meshushim inlet and this data source S. So you see there are in the bottom, these are the values. First, there are not a lot. I mean, there's much more data, but it is only here a few numbers. All of them are integers, and all of them, I mean, without decimal points, and even not only that, but they are all even numbers. That means that there is some, this data source is rounding the numbers, not only to integers, but also to even numbers. So it's just some rounding issue of this measurement source. So you get this strange data distribution. So again, just to emphasize that sometimes the distribution plot, like a violin plot, gives you interesting insights into the data. And actually, the double, like in the, let's say, if you look at the left distribution, which also has like two heights, is really usual for temperature, because there's temperature for winter and temperature for summer, and in the middle there is less. It's a shorter time in which the temperatures are in between. There are cold or hot and less measurements in between. This is also true for air temperature and also for the lake for the stream temperatures. So in general, you can find a lot of from this violin plot, and looking again, it's all looking at the data visually, trying to find interesting things, and the aim is to find mistakes, but on the way you learn also other things about the data. If there is any questions or remarks or or you want to contribute from your experience before we go to the last item of the.
Any questions for Shahar? Yeah, there is a question in the chat. Do you have any suggestions for discrete numerical data instead of continuous?
So sorry again now.
Do you have any suggestions for discrete numerical data instead of continuous data?
I mean, the same, if it is discrete data, meaning it's categorical data, then the same applies for what I in the beginning, the first one about the text data. The best thing is to join it with other, you prepare a list of, let's say, correct data, or let's say the description of this discrete points, one table, and then you join it to your data and make sure that the data does not contain additional things and so on. And you can always use, I think, this unique. If you use the unique command in R, you get only unique results, and you can see all your different discrete data or numbers. I hope I answered the question.
Yes, they say thank you.
Okay, so I'll continue to the last thing. Although, of course, we can. There is additionally, I didn't cover everything about data QC, but I thought this is very useful. Correcting biased data. Sometimes we have data from different sources, and this data can maybe taken in different methods or different locations, and you want to use all the data you have to, because you need it for the model or for the analysis, and you need the full time series. So you want to combine these data sets, but you have to one time series, but they are different. So first, the stages I propose is find a period where you have data from both sources and compare them using fit measures, which we will not do today, but compare them with fit measures, their bias, their R square, or some model efficiency measures like MEF or KGE. Oh, just a minute. Okay, sorry. And look at the data. If you can correct it easily, like linear bias, that's great. That's the easiest way. Okay, we have only a constant bias between the two data sources. That's easy. But sometimes it's more complicated. And one of the tools out of more than one, out of few options, is the quantile mapping. It's a great option, and I think it's easy to use. So and I use the QMAP R package, but I think there are even more options. Okay, so the example is for ERA 5. ERA 5 reanalysis data is a meteorological data. It's widely used when you don't have enough, don't have local measurements or not enough local measurements. So it's a great data source on large scales, but it has a considerable bias on local scales. So just a little bit about bias correction with quantile mapping. The idea in quantile mapping is that you have the distribution of the model, in this case, ERA 5 data is our model, and we have our observation data distribution, and we match each point in the quantile, its quantile to the model to the observation. And and we create a function that transform the model into the observation by the quantile in the distribution. So that's the idea behind it, and you can look at it in the web. In some websites, probably explains better than I am. This is the idea behind it, and okay. So the last exercise is about the bias corrections, and the data is wind speed data. So the data already contains hourly measurements and ERA 5 reanalysis data merged for the same time. So I already prepared the data. Measurements were made in Station A. This is Lake Kinneret, and there is a station in the middle of the lake, which also measures, among other things, the wind speed. Okay, so load the data, make a box plot per source, ERA 5 in Station A. You can plot the overall data per time, separating the two sources. And then, to make it easier, I look at or for the example, I look at the specific time. In the summer, there is diurnal strong winds around in the afternoon, around between 2 and 4 in the afternoon. So we look at these dates in the summer, few dates in the summer, and look at the two sources, the era 5 and station A. So I'm going back to the R studio. Uh, Okay, and I load the QMAP library. We'll need it in a few minutes. And load the wind speed table, which contains, you can see time, data from era 5 and from station A, the wind speed in meter per second. Okay, always when I load data from CSV, so the time is usually loaded as text, so I have to turn it into time. And if we box plot the data, we can see that we have two sources. One is the era 5, it's much lower than the observation in station A. Both of them has maybe unusual values, but you can see that the era 5 data has much lower values. We can also plot in time. The black is the era 5, and the blue is the measurements from the middle of the lake. So we see it is much higher. And if we again look at a few dates in August, this time in 2018, we can see that era 5 catches the diurnal wind, but not the extent that is in reality. I mean, he says it will be up to 4 meters per second, but the winds are up to 12 meters per second.
We have a question in the chat. So
Yeah.
the question is about this time you using as a dot post
Yes.
POSIXCT instead of as dot date. Um,
Yes,
the question is why.
because this contains also it's time, date and time. Okay, this is an hourly. The data is hourly, so it contains both date and time, and R has two methods, I think, as POSIX SCT and LT. You can use the help for these functions, but this is a base R function to transform text into time. Okay, and this is, by the way, a good example of, we talked at the beginning about time zone, because the measurements in station A in the Kinneret is the local time, and I think it is every time we have the change of the daily saving time, I don't remember how you call it. We have to make adjustment for the era 5 time. So yeah, the time zone also is important in this case. So yeah, the POSIX just takes a string from the data and convert it into time format. Okay, so what we see is that again Era 5 does not catch the real strong winds. So what we are using the quantile mapping. And we're taking the mapping, the measurement of the station A with the measurements of the era 5, and we use the simplest method, quantile. There are more parameters you can see. You can look at this package and look for a little in the help. There are many more parameters that you can use and play with, but I use just the standard, the most simple one, and make I call it, okay, BCF is like a function. This is a function. Okay, so I turn it into the bias, the BCF, just my shortcut for bias correction function. Okay, it's the bias correction function. Now we apply it, okay, with the do-Q map, apply the correction to era 5 with this function that we just made. So we have another column. If we go back if we look at the data, now we have a era 5, station A, and another column of bias corrected era 5. And we plot again for these dates in August, and we see the red one is the bias corrected. It is much, much better. They look like data, and now we want to look at the distribution also with the violin plot. So ggplot in a general likes the data in a long format. Okay, because here this is wide format, and long format is just the data and another column for the source, another column for the source, which is it era 5 station A or so I turn it again. This is reshape is in the, I think in the base R. You don't need any package for it. So yeah, the data looks now like this: time, source, and wind speed. So this is how ggplot needs the data. And I plot the violin plot. So we have the station A distribution of the data is up to 15 meters per hour. Era 5, as we remember, is much shorter, and the correction, really the distribution, this is what it does. It matches distribution. So the distribution of the data is almost the same as station A. This is really what we want. Okay. So this is the summary. So what I suggest for data QC is create tools via programming to arrange your data, use merge, and look for NAs to find issues with the data. For now, we also use use duplicate to find duplicates in the data, or unique to find your unique values if it is categorical data or things like that. For daytime data, I suggest you use the ISO 8601 format. For continuous data, we saw create plots and visualize the data and look at it if it is with your expectation. And then we saw one method of correcting bias data. Additional tips that just must mention is the issue of unit of measures. Many times you get data with different unit of measures. Make sure everything is in the same unit of measure, because there can be huge mistakes. And also in the end, we invest a lot of time, but let's make sure it's not too much time, because perfect is the enemy of the good. So decide when your data is good enough. And that's it. I asked one of the AI programs to make me a summary slide, and this is what he did. So yeah, if you have any questions or remark, let's see if I can open the... here.
That's great. Thank you, Shahar. It was amazing. Now I'll stop the